Hi, in this video I'm going to show how to train a reinforcement learning DQN agent to keep a vehicle in its lane using a Simulink model and parallel computing. Keeping a car in its lane is a problem that has become more common recently. Some cars like the Toyota Corolla that's going to tell you when the car goes out of the lane. There are many cars that have similar technology, but the problem in this example is going to be controlling automatically with a reinforcement learning agent that the car keeps in the lane. So the car can move in two directions: to the front, longitudinal direction, which is considered constant in this problem at 15 meters per second, and also the angle, which is controlled by the steering wheel, and that's the one that the reinforcement learning agent is going to control in this problem. So the episode of training is going to end if the vehicle goes outside of the lanes. So if the lateral deviation goes above 1, the absolute value, then the episode is over. For the reward, we're gonna not only consider the lateral deviation, but also the angular deviation. So you want the car to go straight, so you want the angle to be 0. So if it is something different than 0, then you get a penalty. Also, the speed of the lateral deviation, the rate of change of lateral deviation, the rate of change of angular deviation are going to be considered as negative in the reward. But of course, the lateral deviation is going to take the biggest penalty because that's going to be your game over if you get out of the lane. In addition to that, the amount of steering that the agent is going to do is going to be considered as a penalty in the reward. It's like when you're driving in your car and you want to keep the car in the highway in the lane, you do the minimum possible steering. Or you always do some steering, but it's very minimal. So if you do a lot of steering in the highway, that's not good. So that's why it is considered as a penalty in the reward. Before going into the example, I'm gonna give you some background of the DQN agent. That is Deep Q network. This is an agent that depends on the Q function. The Q function is a function that is gonna predict the accumulated reward of the agent. So basically, the agent is gonna base its actions, its decision solely on this function. So it's gonna go in the direction that is gonna maximize the long-term reward, which is the value predicted by this Q function. So the DQN agent is gonna work for continuous or discrete observation spaces, and it is gonna work only for discrete action spaces. So you may wonder, how can this agent be used in this example? Because the steering wheel is something that is continuous. Well, you discretize it. So you have, let's say that in this example, the steering wheel can go from 0 to negative 15 degrees or 0 to positive 15 degrees. So you have that range between negative 15 degrees and 15 and divided by 31. So you have 31 possible actions. So now your action space becomes discrete. So that's what the problem does for this. Let's take a look at how the DQN looks relative to other agents. So it's an off-policy agent, doesn't depend on the policy. So it doesn't have an actor, just a value, is value-based. And one detail about parallel computing in training, in reinforcement learning training, that I would like to clarify relative to my last video is that there are two types of ways to compute the experiences and the gradients in these agents. One of them is called experience-based parallelization, and the other one is gradient-based parallelization. In the experience-based parallelizations, you're going to have a client that is going to launch a set of workers. Let's say that you have 8 cores in your machine. So the client is going to launch 8 workers. So those workers in the experience-based parallelization are going to compute the experiences. And then those experiences are sent to the client, and it computes the gradients with them. And then the gradients are used to update the parameters of the network, and then the agents are updated. Okay, and then the other one is the gradient-based parallelization. In the gradient-based parallelization, the workers in parallel compute the gradients, and then the client gets the gradients, gets an average, and updates the agent, and then the workers keep on going with the updated agent. Okay, so as you can imagine, computing the experiences is less sensitive than computing the gradients, because in the gradients you have to average them. So in addition to this, the parallelization can be done asynchronously or synchronously. Synchronously means that the workers need to before going to the next phase, need to all the workers to finish, because they have to synchronize with the client. Asynchronous means, let's take for example in the experience-based parallelization. So that one can be both synchronous and asynchronous. So because the experience gets sent to the client computes the gradients, updates the agent, and the workers keep on going. You update the workers and create new workers, and it doesn't matter. It can be synchronous or asynchronous, and as you can imagine, the asynchronous should be faster, because the synchronous can block the processes, which makes them more slow. So you might prefer asynchronous. But in the case of the gradients, the gradient-based parallelization, that you have to take the average from all the workers, in that one you have to synchronize. It has to be synchronous parallelization. So in summary, the on-policy agents have to use a gradient-based parallelization, and the DQN, which we're going to use in this example, and the off-policy agents are going to use experience-based parallelization. So these guys here can use both asynchronous and synchronous parallelization, while these ones have to use synchronous parallelization. Okay, now let's go to some details of the DQN agent, of how the training, the learning is done for this agent. So as mentioned before, it depends solely on the Q function. So it's gonna take the action that is gonna maximize the long-term reward according to this function, how that function models it. Okay, so in order to update the parameters of the network, this is a neural network that is gonna based on the observations, is gonna predict the expected long-term reward for a particular action and a particular state. The state is basically observation. Given the state, it's gonna and the action, you're gonna get the expected long-term reward. Okay, so how the parameters of that network is updated? You have two options. This agent can be double DQN or regular DQN, and you're gonna compute the long-term reward, and you're gonna subtract it by the predicted one. So the difference is gonna be the loss, and that loss you compute the gradient, and with the gradient you update the parameters. Okay, so in addition to that, you can see that that difference is summed over all m's, and what are the m's? Are basically the mini batch size. This is the mini batch size that you configure in the options. Okay, so how do you compute the expected reward? You can see the formula here is almost the same between the two, but notice that the reward is computed with the reward you already had through all the steps in your episodes, and the one that is predicted by the target. So you get the action that maximize for the DQN, the action that maximize with that target network, and also you have this discount factor. This discount factor is configured also in the agent. It's basically that the more time passes, the less reward you get. It reduces the reward as time passes by, and that basically is a way to say to the agent, hurry up, try to finish as soon as possible, because the more you take, the less reward you get. Okay, so notice that it's using the target here to compute the actual reward, but then the one that you're training is compared against another network. So you have two different networks. They have the same structure, the same network, but different parameters. So it's like you predict the action. When you take the action, you use this regular network. But when you do the comparison of precision, you use the target. And the target is not updated with this, only this one. But the agent is configured to update the target at a given rate. And this is configured. You have the target smooth factor is how you are gonna, you can see that you're gonna merge the value of the regular network with the target network, and this is the factor that you configure with this smooth factor. And also you have target update frequency, which tells you how often you take this formula and update the target. So it's like having two networks. One of them is to compute the reward, another one is to get the action. So that double network helps to get better training for this particular agent. And the difference between the DQN and the double DQN is that in the double DQN, you notice that the action, well, this regular DQN is going to take the action based on the target network actually to compute the reward. But the double DQN is going to take the action based on the regular network to compute the normal reward. Yeah, so that's a slight difference between the two, and you can choose also that in the agent parameters. Okay, let's go to example. Okay, now we are in the MATLAB session. First are the physical parameters of the model, which is the mass of the car in kilograms, the moment of inertia of the steering. Also, you have the cornering stiffness of the front and rear tires, and the longitudinal distance of the center of gravity for both the rear and front tires, and also the longitudinal velocity, which, as I mentioned before, is 15 meters per second. So we don't care much about the longitudinal velocity, but it does affect the computations of the lateral deviation and angular deviation, so that has to be taken in consideration, but we don't control it in this problem, only the steering angle. Okay, so we have a total of 15 seconds for the simulation and a step size of 0.1 seconds, and the steering angle goes from negative 0.5 radians to 0.5 radians. So again, this range is going to be discretized, and this is the raw is basically to model the curvature. There's going to be a curvature to make the problem a little bit more interesting. You have the initial lateral deviation and the initial yaw angle deviation, the angular deviation and the lateral deviation. So the goal of this problem is basically to bring those two to zero. That's what the reinforcement learning agent is going to do in here. Okay, so this is the Simulink model that we are going to use for the environment. Simulink is a very good environment for simulation, so it fits very well to this type of reinforcement learning problems. So you can see in here, this is the block for it's called R agent. It is red because we have not created the agent yet. So this model consists of the dynamics of the vehicle, which in this case are very simple for the purpose of this example. And then we have some sensor dynamics to compute the observations, which is the observation is problem is the lateral deviation and relative yaw angle, which is like the angular deviation. And also the derivatives of both of them. And in here, we're going to compute the integral of both of them. So you have a total of 6 observation variables: a lateral deviation, yaw angle, relative yaw angle, and the derivatives and integrals. Okay, so let's take a quick look at but first, before going there, the observation is gonna be used to check, okay, if you're outside of the lane, then the simulation is done, and with the observation you compute the reward, and also you pass the observation to the agent, because the agent is going to take an action based on the observation and the reward. And then no, actually the observation should be enough to take the action, but the reward is part of the training. It's for training purposes. Okay, so the action that is going to be taken is the steering, and the steering is passed to the dynamics, and that dynamics is going to give you another lateral velocity with a new angle. And then the steering angle, the steering action is going to also be considered for the reward. That's why it is fed back in here. So let's take a quick look at the vehicle dynamics. So the input is the longitudinal velocity, as mentioned before. This is just constant 15 meters per second. And the action, the steering angle, this is the action that comes from the agent. The output of the dynamic system is going to be the lateral velocity and the yaw rate, the rate of change of the angle of the vehicle. So both velocities, we get them by doing the integral. So what comes at the other side of the integral is the acceleration. And to compute the acceleration, like the Newton formula, F is equal to m multiplied by a. To get the a, the acceleration, in order to compute the velocity, you have to divide the force by m. So here's how you compute the force using the stiffness and also the length of the distance of the center of gravity of the front and rear wheels. So you divide that force by the mass and you get the acceleration, and basically with that you compute the lateral velocity. In the case of angular velocity, you have the angular acceleration, and instead of using mass, you use the moment of inertia. You divide by moment of inertia to get the angular velocity, and it's basically the same. Okay, so with that, now we need to compute the lateral deviation and relative angle. So for that, it has to be taken into account the curvature of the road and also the longitudinal velocity. So for the case of the yaw rate, this is relative to the curvature, so that has to be taken in consideration. So with that, you get the relative, the derivative of the relative yaw angle. So we have easily the speed in here. Then we apply the integral and we get the deviation, the actual deviation. And then the actual deviation plus longitudinal velocity and lateral velocity are computed together to get the lateral deviation. This is the but then this is a speed. We have to integrate to get the actual lateral deviation. This is the variable that matters the most in here. Okay, so we have the 4 variables that are fed to here, and to get the observation, we just feed them forward. These are the observations, but in addition to that, we have to do discrete integration. So we use this instead of use 1 divided by s, which is the continuous integration, we use the C transform rather than the S transform. So that is C minus 1. So with that, we get the integral error, discrete integral error, and basically pass on the positions and velocities. Okay, so for the reward, well, first, the episode is going to be over when the lateral deviation goes above 1, the absolute value goes above 1. And as mentioned before, the steering action is going to be considered for the reward, so this is going to be the reward. And as you can see, this is the lateral deviation, and that's the most important, so it gets the biggest penalty. Everything is positive in here, but as you can see outside, it's going to be multiplied by negative, so all the reward is negative. There's no positive reward in here. Everything is negative, so you're going to give a penalty for all those 5 variables. So again, if you deviate, this is what's going to kill you in the problem, so that's why you give the highest reward. You don't want to get out of the lane, and of course you don't want your the angle of the car to be that much, so you give a penalty for that. And also you give a penalty for the velocities of the angular velocity and lateral velocity. You don't want those. You want those be close to 0. That's why you have this. And of course you want to move the wheel as less as possible, so you have a penalty for that as well. Okay, so that's your reward, and the reward is fed to the agent plus the observation and the terminal. So now that we have that we gave this overview through the model, through the environment, then let's create the environment and the agent to do the actual reinforcement learning. So first, let's get the path to the reinforcement learning agent block, which is RL. This is the name, RL agent. and the name of the model. So with that, we get the path in the model to the block, which is this one. Okay, so now let's create the observation information, which is numeric spec, because this is contiguous. We got the lateral deviation, angular deviation, their velocities and acceleration, so we have a total of 6 variables. We don't care about the limits, so the limits are both positive infinity or negative infinity for everything. We put a name and a description for the observation object, and for the action, we want it to be between negative 15 degrees and positive 15 degrees, and we convert to radians, and then divided by, we're gonna have 31. We discretize this, and you can see that this is a range of discrete values. We have a total of 31 values that go from negative 0.26 to positive 0.26, including 0. And we're going to use RL finite spec. This is numeric because it's continuous, and this is finite, so RL finite to get the actions. We put the name to it, and these are our finite actions. So we pass the observation, the actions. We're going to create the environment. We have the agent block, which is the path, and the model, the Simulink model. So we use basically the Simulink model as a simulation environment. And then we need a reset function, because for the reinforcement learning training, we have for each episode we want to randomly start from the beginning. And as you can see in here, the lateral deviation, we integrate to get the lateral deviation, but that integral is going to have an initial value, this E1 initial value. The same goes for the relative yaw angle. We're going to integrate from the rate of change, and the integral is going to have an initial value. And those two values, those initial values, are the ones that we're going to reset in the reset function. So that reset function has to be provided through this lambda, but this lambda goes into a function that we can declare anywhere, or we just can keep it as a lambda. So basically we set the initial values randomly for that deviation, and yeah, it's gonna be used for each episode. And now we have the environment. Now let's create the DQN agent. First, we need to know the number of inputs for the network, for the Q network, which is going to be 6, the number of observations. We're going to have 120 neurons for the layers, for the internal layers, and the output is going to be a number of actions, which is 31 possible actions. So we are going to use a very simple network, a linear network, using fully connected layers and ReLUs, and we use this RNG0 to set the seed of randomization, because as you can see, functions like this one are going to randomize. So to make this example reproducible, we use that, but you don't really have to do that. So let's create the DL network based on the layers that we created here, and we're going to provide the summary. Okay, so now we can plot it, but I'm going to use this analyze network function, which is a little better. You can see the network is pretty simple. 6 observation inputs, and the output are the action, with 120 internal layers plus ReLU for regularization. Pretty basic deep learning network. So now we have the Q network with the DNN. We have the observation and the action, so we are going to create the Q value function, which is going to be our critic. And this agent, again, doesn't have an actor, just needs a critic. So we're going to provide optimizer options for training that network, which is the learning rate of the network, 1 to the minus 4, and also we're going to put a threshold to the gradient, so the gradient doesn't explode. And we have some regularization as well to help it to generalize. So we have the critic options, we have the critic. So no, we haven't created the agent yet, but we need the DQN agent options. So we have the sample time. We're going to use double DQN. As I mentioned, there was a slight difference between using double DQN and regular DQN, is how do you get the action to compute the actual reward for getting the loss, which basically is used to train the Q function itself. So yeah, this is some variant version of the algorithm. So we pass the critical options, the experience length, buffer, and the mini batch size. This is to get the experiences that are gonna be used. How much experiences are you're gonna use to compute the to do the training on the network. So yeah, so we have the options of the agent, and this epsilon greedy exploration strategy is basically the decay how, because initially you don't want to be greedy, you want to explore as much as possible. It could be randomly, or it could be to explore sections of the experience that lead you to better distribution of your training data. It could be any strategy, but anyway, you don't want to be greedy at the beginning. So that's what this epsilon decay is for. So at the beginning you start exploring a lot, and then that is gonna decay, and eventually you get very greedy to maximize the reward. So that's this is what controls the exploration strategy of the agent. Okay, so we have the agent options, we have the critic already, which is the Q value function, and then we create the DQN agent. So now we have the agent, we have the network, the environment. So now we need the training options for reinforcement learning, which is basically that we're gonna stop after we get a reward of 100. This is we're gonna stop also if the criteria is bad, and the maximum steps that we're gonna do, which is basically 15 divided by 0.1, which is 150. Whoops. Okay, which is 150. Yeah. So this is the maximum number of episodes is 10,000. This example takes a lot actually. So we're gonna try plot the process, and yeah, actually this is gonna stop when the reward is -1. So as mentioned before, there's no positive rewards, there's just negative rewards, and you want to minimize the reward, because the reward starts at negative a lot. You get a lot of penalties, and you want to minimize that penalty. So this is for saving the agent. So yeah, this is to configure how you're gonna save it. Okay, so now comes the parallel part. The parallel part is very simple. You're gonna say, okay, we're gonna use parallelization, and as mentioned before, this type of agent is an off-policy agent that can that uses experience-based parallelization, which can be both synchronous or asynchronous. Asynchronous, of course, there's no blocking, so I would prefer that for parallelization. So that's what is picked up in here. And training this, as you can see in the article, is gonna take 1 hour. So it took me, this is the picture from the training. It took me 1 hour and 20 minutes to do the training. You can see that at the beginning it was very bad, -500, but eventually converged to -1 to basically bring the penalty to 0. And you can see some similar pattern in here, that you start very bad and eventually get to almost 0. But since this takes a lot of time, I'm just gonna load the train agent to avoid using 1 hour of computation time from my computer. And yeah, we can now simulate the agent to get the reward. So oops. So let's take the options, maximum steps. We're gonna do 150 steps, and let's just simulate this. And sim is a method of the environment, so you can do it like this. So it's a method that takes as input the agent and the simulation options, and it's gonna give you the experience. And we're gonna see how the experience progresses. That experience is gonna give you the reward. And now we have it. You can see experience. From the experience we get the reward and the data. And in the data you can see that at the beginning it should be very bad, negative something. Let's compute it again and get the reward again. At the beginning it's very bad, usually it's very bad. It depends on the initial value of the lateral deviation, but eventually once the lateral deviation gets close to 0 and also the angles get close to 0, then the reward gets close to 0, which is good. So now let's simulate it, but in this simulation we're gonna put an initial deviation, lateral deviation of negative 0.4 and an angle deviation of 0.2. Okay, and now we can use the sync command, but since we're in Simulink we just can't play here. Just play it, and when we play it, this is gonna have already open. Let me just run it again. Okay, the simulation finished, so let me bring the plots. Okay, let's bring the plots. Here's the lateral deviation, the angular deviation, and the steering wheel action. So you can see at the beginning that we have a negative 0.4 lateral deviation, and it's basically controlled like a regular control system, is brought to 0. The same goes for the angular deviation, which starts at 0.2 and is controlled all the way to 0. And at the beginning, as expected, the steering angle is high and eventually it gets very small, like what happens to us when we drive in the highway, that you just move the steering wheel a little bit to keep it straight. So that's effectively what the agent did. And so that's all for the problem, for the example. Thank you very much.